Can moons have their own moons? Moons are amazing natural satellites that orbit planets and other objects in space. While most moons orbit planets, some moons also orbit asteroids and Kuiper belt objects. But are there moons of moons? Is it possible to have such a system in which moons have moons orbiting them? The answer to this question is more complicated than it looks. But don't worry, we have got that covered for you in this video. Let's try to look at this question from the lens of science and theory. Moons are thought to be formed when a planet or object is hit by a large object, such as a comet. The impact creates a debris field that eventually coalesces into a moon. Most moons are less than 1/10 the size of the body they orbit. In our solar system, only 2 planets, Mercury and Venus, do not have moons. Why? Don't worry, we will answer that question for you later in this video, and it will help us get an insight to the original question we asked about moons of moons. The gas giants are big and stable and have dozens of moons orbiting them. Can the moons of all these planets have moons? The answer is yes and no. Don't be overwhelmed by our answer. Just follow along in the video and you'll understand. Most planets have moons around them. Even some Kuiper belt objects and asteroids have natural satellites orbiting them. However, there are no known moons of moons out there. It may not be because we're just unlucky. There may be some fundamentally important rules of astrophysics that make it extraordinarily difficult for such an object to stably exist. One reason moons of moons might be difficult to form is because moons are generally much smaller than the body they orbit. This means that the gravitational force exerted by the moon on the body it orbits is much weaker than the gravitational force between the body and the object it orbits. As a result, moons are constantly being pulled out of orbit by the larger body they orbit. Another reason moons of moons might be difficult to form is because they would be constantly bombarded by debris from the larger body they orbit. This debris would eventually break up the moon, making it difficult for it to maintain a stable orbit. But that doesn't mean that they cannot exist. When all you have to consider is a single huge object in space, everything appears simple. You'd think that because gravity is the sole force at work, you'd be able to put any object into a stable, elliptical, or circular orbit around it. Under that configuration, you'd think it'd go on indefinitely. However, there are additional forces at work, such as 1. This item may have an atmosphere or diffuse halo of particles surrounding it. 2. This item is not necessarily stationary, but it can spin, perhaps quickly, about an axis. 3. And that this thing may not be as isolated as you first thought. When objects revolve around this central mass, they are affected by the presence of an atmosphere. Even an incredibly diffuse atmosphere can cause orbiting bodies to have to contend with atoms and particles. This can lead to the objects colliding with the central mass. The first aspect, an atmosphere, is only relevant in the most extreme of circumstances. Normally, an object orbiting a vast, solid world with no atmosphere would simply avoid the object's surface and might continue to revolve about it indefinitely. When you add the presence of an atmosphere, even if it is quite diffuse, any circling things will have to battle with the atoms and particles that surround the center mass. This can lead the item to alter trajectory and crash with the core mass in some situations. As a result, the presence of an atmosphere must be included when computing object orbits. It is commonly thought that atmospheres have an end beyond which space begins. However, in reality, atmospheres simply thin out as elevation increases. Earth's atmosphere, for example, extends for many hundreds of kilometers. The International Space Station orbits within Earth's atmosphere and will eventually decay and meet a fiery doom unless it is continually boosted. Similarly, over the solar system timescales of billions of years, orbiting bodies need to be a certain distance away from whatever mass they orbit in order to be in a safe orbit. This is because the atmospheres of celestial objects can extend much farther than previously thought. Therefore, when planning missions to other planets or moons, it is important to take into account the possibility that their atmospheres may extend much farther than previously thought. Looking at our second factor, we know a celestial object can rotate. This holds true for both the huge mass and the smaller mass circling it. There is a stable position where both masses are tidally locked to one another. They always have the same side facing to one another. But any other arrangement will result in some torquing. For the locking to occur, this torque might spiral the two masses inwards if the rotation is too slow, or outwards if the rotation is too quick. In other words, most satellites do not begin in the optimal configuration, but there's one more aspect we need to consider before we can get to the topic of moons and determine where the trouble lies. The fact that an object is not isolated is extremely important. It's far simpler to maintain an item in orbit around a single mass, such as a moon orbiting a planet, a tiny asteroid orbiting a huge one, or Charon orbiting Pluto, than it is to keep an object in orbit around a mass that circles another mass. This is a significant element that we rarely examine, but consider it from the perspective of our innermost moonless planet, Mercury. Mercury's orbit around the Sun is relatively quick, and as a result, both the gravitational and tidal forces acting on Mercury are very large. If there were another object orbiting Mercury, the number of factors at play would increase significantly. The wind from the Sun, the outward flow of particles, would crash into both Mercury and the orbiting object, causing disruptions to their orbits. Additionally, the heat that the Sun applies to Mercury's surface can extend Mercury's atmosphere. Even though Mercury doesn't have much air, particles on the surface can get heated and thrown into space, resulting in a tremendous but non-negligible atmosphere. Finally, the third mass present creates a situation where Mercury could become locked to the Sun due to the tidal forces present. As a result, Mercury's orbit is complex and fascinating, making it an interesting object to study. This means that for any satellite of Mercury to exist, there are two locations. If the satellite comes too close to Mercury in any of the following ways, like the satellite isn't rotating fast enough for its distance, Mercury isn't revolving fast enough to establish tidal lock with the Sun, it's subject to enough friction from Mercury's atmosphere, the satellite will crash onto the planet's surface based upon the above conditions. Although a satellite orbiting Mercury may experience some stability due to the planet's gravity, there are a number of factors that could cause the satellite to be ejected from the orbit. If the satellite is too distant from Mercury, it may be pushed away by the planet's gravity. Additionally, if the satellites rotate too quickly for its distance, or if Mercury rotates too quickly to become locked with the Sun, the satellite may be ejected. Finally, perturbative effects from other planets or heating from the Sun could also work to eject a tenuously held moon or satellite. If that's the case, how do planets have moons if they are orbiting the Sun? As we've mentioned above, a three-body system is never truly stable. However, there are conditions that make it more stable on timescales of billions of years. One of the most important factors is the distance of the planet or asteroid from the Sun. If it's too close, the solar wind, sunlight, and Sun's tidal forces will all be too strong and will destabilize the system. If it's too far away, however, the satellite will be too loosely bound gravitationally and is likely to be kicked out by the other gravitational or mechanical interactions. The sweet spot is somewhere in between, where these disruptive forces are minimalized. If the planet, satellite, asteroid is sufficiently far from the main body, tidal, frictional, or other processes will not lead it to in-spiral and join with the parent body. Under these conditions, a three-body system can be stable for billions of years. As one might expect, there is a sweet spot for moons to exist around planets, a few times the planet's radius away, but near enough that the orbital period isn't too long, still much shorter than the planet's orbital period around its star. So, with all of this in mind, where are our solar system's moon satellites? The largest moons are the best candidates we have for housing satellites. Satellites of moons are much more likely to be in stable orbits and to be tidally locked to their parent world. However, none of these are currently classified as moons of Jupiter. There is still hope that we may see one in the future, but it is unlikely. The gas giant worlds are pretty stable and they are located far away from the Sun. They have plenty of moons, many of which are already tidally locked to their parent world. The best candidates would be as large as possible, relatively far enough from the parent body to reduce the risk of in-spiral, but not so far away that an easy ejection is conceivable, and well separated from any other moons, rings, or satellites that may disrupt your system. The moons of gas giants like Callisto, Ganymede, Iapetus, Titania, and Oberon can be some of the best candidates in our solar system to have moons. But with all that said, it's fascinating to think about the possibility of a moon orbiting a gas giant planet, but the conditions required for that to happen are so extreme that it's unlikely we'll ever find one. The moon would need to be orbiting at a great distance from its planet, be isolated from other large masses, and have a high escape velocity from the surface of the planet. Based on these criteria, Iapetus and Triton are the most likely candidates for having a moon. However, even if they do exist, they would be very difficult to detect and study. So while the idea of a moon is intriguing, it's probably best to not get our hopes up too high. Or it could be that our understanding of this concept itself is wrong, and our greatest shot will be in the outer regions of the Kuiper belt or possibly the Oort cloud, where we simply have many more chances than we'd ever have in our solar system. Whatever it might be, the idea of having such complex systems itself is interesting. And even if we don't find such a satellite in our solar system, it might be that they occur in a few rare star systems. So what do you think about the concept of moons having moons? Can they exist in our solar system? Let us know in the comments below, and be sure to watch our other videos about our solar system through the YouTube end screens and playlists.